Let's practice our conservation of energy skills with a skiing problem. So if you imagine a skier on a slope, and we'll make it frictionless, we want to know what their final speed is when they get to the bottom of the slope. And we're given that the skier starts from rest, and that we can ignore things like drag, friction, and heat transfer, all of which would complicate this problem. The slope is 30 degrees, and the distance that the skier travels is 12 meters. Then we'll define the positive z direction to be upward and get started. Conservation of energy tells us that the change in total energy equals Q minus W, where the change in total energy is the sum of the changes in kinetic, potential, and internal energy, and Q is the heat transfer, W is the work. Well, we were already told that we can ignore drag, friction, and heat transfer, so actually that combination tells us that really Q and W are both zero in this problem. So there's no heat transfer, and no work being done by some external force, such as drag or friction, which would be the most likely suspects. We also expect that the change in internal energy is zero. This might be a little tougher to see. If you think of the change in internal energy as being a combination of things like the change in the skier's thermal energy, but also any changes in them microscopically, well, whatever's going on, it's not going to be important to changing things like the skier's speed. So we can just assume that that change is very small compared to any other changes in the system. That reduces our conservation of energy expression to delta Ke plus delta P equals 0. This is a relatively straightforward form of conservation of energy, and you may also know it alternately as the conservation of mechanical energy. Well, we can put in the forms for kinetic and potential energy differences, and you'll notice that I put ears on the V's. This is to distinguish velocity from volume. So if you see a V with ears on it, that means it's a velocity. V without ears is a volume. We will encounter problems that have both velocities and volumes. So that's the full expression for the sum of the changes in kinetic and potential energy. Now we just need to sort out what all of these terms are going to be. Let's cancel a factor of mass first. And we want to solve for the final speed. Well, the final speed is equal to the magnitude of v2, so we want to rearrange for that. And we can go through and find an expression just for v2's magnitude, which is the square root of v1 squared minus 2g times z2 minus z1, where z is just the position of the skier in the z direction. Let's go through these two terms slowly. So first let's tackle v1. We're told that the skier starts from rest, and if you remember, the convention in this class is that 1 happens before 2, so v1 is the initial velocity of the skier. That tells us that that must be 0. So we fill that part in and we fill in 2g. Getting z2 minus z1 is a little more work, but we have enough information. We know that the skier traveled downslope a distance of 12.0 meters, and that the hill is angled at 30 degrees. So we can apply some trigonometry and figure out that the distance the skier traveled in z must be 6.0 meters. But z2 minus z1 is not 6.0 meters. If you think about it, z1 is where the skier started, z2 is where they ended up. They have a negative z displacement that actually needs to be minus 6 meters. If you got that sign wrong, you'd have a negative under your square root, which in a problem like this is a clear indication of an error. So now we go through and figure out that the final speed of the skier at the bottom of the slope is 10.8 meters per second. Now you could just as easily have gotten that answer by applying the equations of motion for constant acceleration that you learned in an introductory physics class probably in the first few weeks. The great thing about conservation of energy, though, is that it also lets us solve problems that you would not easily be able to do using the equations of motion or even forces. So let's consider what happens if the shape of the hill changes. So it's still frictionless, but now there's a little bump in the middle. If you think about it, nothing that we did to solve this problem made any assumptions about the shape of the surface. The key details were the z displacement was negative 6 meters, the skier started from rest, and we could ignore drag, friction, and heat transfer. All of that is still true, all of our work is still true, the final number is the same, the answer is still 10.8 meters per second at the bottom of that slope, so this is independent of the hill shape. In my opinion, this is where conservation of energy really shines. It lets you do problems that would have been really tough to do any other way.